Hello everybody, we're back in section 3.2, picking up again with function rules where we were last time. Um, Basically, the symbols f of x are a way to abbreviate the notion of using a function named f on an input x when you've defined the rule for the function to be this. Basically, you read x here as input. 3 times whatever the input is squared minus 5 times whatever the input is plus 1. When you get done with that, you'll have your function value because it's defined to be that, and that's your output. That's how a function relates its input to its output. So using function notation, we often call this x a dummy variable. I mentioned that a few slides back. All it's doing is really acting as a slot. It acts as a blank to fill things in or a box to fill things in. It tells you where to put the inputs. That's all it does. It just marks where to substitute in the input. And this x, since it's doing that one limited thing, is often called the argument. This whole idea of function was part of what built the field of computer science. A lot of programming languages are built around the mathematical concept of function. So as we've seen before, the parentheses don't mean multiply. You're not trying to, with this x, you're not trying to solve for a variable or anything. All you're doing is trying to get input substituted into the correct place. So it's a placeholder. So if you say this is the standard mathematical way of saying it, we think of that x as just a box. And whatever appears in this box is substituted over here. Whether it would be a simple thing or a complicated thing, whatever appears in this box, and the parentheses tell you where that box starts and stops. Whatever's here goes into each copy of the variable over here. And that's called evaluating a function. So when you do this, you evaluate the function. That's an important keyword. So here we have a couple of examples. We'll use the same function as we've seen on the past couple of slides. If you said this, that f of x is defined to be 3 times the input squared minus 5 times the input plus 1, then if your input is 42, you replace every occurrence of the x with a 42. So the x's just became 42s. If you say that you're going to do f where 5/12 is the input, then the x's become 5/12. At this point, you really don't worry about what the square or the 3 or the -5 are doing. All you're caring about is getting the 5/12 into the input slots. And there were 2 input slots here. You've got to get the value into that. It doesn't matter how complicated the input is. This is a lot more complicated than we would deal with in Math 098. But here's a big messy expression in the argument that goes into each of these input slots. It's 3 times the input all squared minus 5 times the input plus 1. Now notice for several of these I put parentheses around the inputs. That's a great way to head off any order of operations mistakes. You never can go wrong surrounding your inputs with parentheses. So sum it up. Whatever appears in the argument as an input is copied exactly. So input goes to each copy, each instance of the dummy variable in the rule. Use parentheses around those inputs. They never hurt. So when you've done that, you've evaluated the function often after that we simplify. After you've done the function evaluation, then you have an algebraic expression, and you can treat parentheses and variables just the way you've always treated them before. So, for instance, here's an example. We've defined the function f to have the rule that if for whatever its input is, you square the input, multiply by 2, minus 3 times the input, plus 1. So, f of negative 1. Notice that I write that down below. This is the formula. This will be the substitution step. It's going to be 2 times whatever the input is squared minus 3 times whatever the input is plus 1. In this case, my input is a negative 1/2. So I put that in without thinking about what's going to happen next. I simply want to get the input into each of the input slots. Then I've essentially evaluated the function. I've done what the function rule said. Now I'm going to simplify the resulting arithmetic. A half squared is a fourth, so I'll end up with 2 over 4, 2 fourths. A negative times a negative makes a positive. I'll end up with 3 halves plus a 1. 2 fourths is 1/2 plus 3 halves. 1 is 2 halves. In order to add the fractions, I have to have a common denominator. Now, since everything is halves, I can, instead of thinking as 1/2 plus 3 halves plus 2 halves, I can think as 1 apple plus 3 apples plus 2 apples. And 1 plus 3 plus 2 is 6. So I get 6 halves, which reduces to 3. So officially what we did here was we evaluated the function in the first step. The remaining steps were simplifying. Simplify the, in this case, arithmetic. Sometimes you have some algebra to simplify.